Hi, I'm MyungJoo from Samsung, and this is a collaborated work with Ingi and Chanu. So we have been optimizing the power consumption of the mobile devices and wearable devices. So in this paper, we have experimented with the wearable devices like Gear 2 and Gear S. So let's look at how the devices have been evolving in the mobile and wearable industries. So this is some short, brief history of devices. When we look at the display devices, the resolution has been increasing a lot. So, and 5 years ago, we had like 800 by 480, and right now we are approaching UHD right now. So the resolution has been increasing a lot, and the memory bandwidth caused by the display is increasing as well. So 5 years ago, it was about like 100 megabytes per second, and it is approaching now about 1 gigabytes per second. So we are using a lot of bandwidth of memory, and it is causing a lot of energy consumption in the devices. So we have been applying device mechanism in the memory interface and its buses. However, what if we can just apply the bandwidth reduction instead of DVFS, so that we can apply DVFS more aggressively, and we can just reduce all the energy consumed by the memory traffic. And another aspect is that the resolution of the wearable devices is not that high, but such devices has also small batteries. So any small percentage of power reduction can be translated into the longer battery life expected. So even small improvement is welcomed in this kind of devices, and we were focusing on these wearable devices for our approaches. So when we look at the display for power management, it has been not very well addressed. So if we look at the other energy hogs like CPU, GPU, or memory, or even network devices, there have been many approaches to reduce the energies in such kind of device components. But for displays, practically not much has been done for the display devices, although these display devices consume a lot of energy in the devices. So what we have done in the research, well, there have been many research approaches for the display power consumption. And they work in theory, but in practical, either it cannot be used by the industry, or the side effect is too critical. So for example, if we try to adjust the color depth dynamically, it affects the image quality, and the quality assurance team will not allow us to use this scheme to simply reduce the energy consumption. And also, if we try to do the dynamic backlight brightness, which reduces the power consumed by the backlight devices of LCD displays, because these backlight devices has longer latencies, we cannot use that for frame by frame. So we need to expect such longer latencies, and the image quality also degrades with these approaches. So we cannot use that as well. And this does not work for AMOLED displays. So organic LED displays cannot use this approach as well. If we try to do the dynamic display refresh rate, it also affects the image quality, and we cannot use that. So, and there are other mechanisms like compression or skipping duplicated transmissions. But however, if you try to use this, you need to read the whole frame buffer for each frame, which will consume more energy than you save the energy. So you will require additional hardware that will do this for you instead of CPU, or your overlay will just eat up all the benefit you wanted. And there are other approaches proposed by ARM, and they are using these techniques in their new hardware. Well, they reduce the memory bandwidth in between some of their specific IPs. However, you are required to use their own hardware, which is licensed. That means that you need to put more money when you make your hardware, and the benefit from those hardware approaches is restricted to a small portion of any operations or software stacks. So our observation in display power consumption is that in order to reduce such power consumption, you need to tackle the bandwidth between the devices or from memory to processors. However, some may say that if we get a better memory interfaces, which will require less energy for each byte, then then we can just solve the problem. However, it is not going to solve things because newer generation of memory interface will give you lower energy per byte. But with better memory, you will have more bandwidth, and you are going to use more bandwidth because it is available, and applications will use that additional bandwidth. So in overall, the energy consumption, the power consumption of the memory will be increased with newer memory architectures. So we cannot just rely on newer memory architectures. So to practically reduce display power, we need to tackle the bandwidth. We need to mind the overhead, because if you just try to look at each frame, that will just consume every benefit. Hopefully, we don't want to add any hardware because of the cost. Hopefully, we don't want to modify the operating system too much because we want to keep the compatibility and we want to keep the transparency for the applications. So keeping in mind such principles, what LPD has done. So I'm going to introduce what we have done to reduce the power in the displays. Well, firstly, looking at the hardware architecture of general mobile or wearable devices, things are like this. Processors will draw any images into the memory, which is depicted as number 1 here. And then this image will be transferred to this display controller, which is number 2 here. And then this display controller will control the buses and the panels. So it is transferred to the display panel via the display bus in number 3. Then this display panel will just draw that image into the screen. And here you are seeing the internal memory, which is in the display panel, and it is supported by I-80 architectures. Well, you may think that I-80 display panel is not general enough, but recently the mobile or wearable industries has been using this I-80 architecture. And if you look at Samsung device from Galaxy S4 or later, we have been using I-80 display panels for any flagship models or wearable devices. So we may think that I-80 is general enough for modern devices right now. So we wanted to save the bandwidth between the DRAM to the display panel, which is depicted by number 2 and 3. So if we send the updated parts from the main memory to the internal memory of display panel, then we can save the bandwidth, thus we can save the energy, because we have the previous frame in this internal RAM. However, the problem is that how can we know which part is updated and which part is not updated? If you try to do that with comparing with previous frame, then the energy consumption is too high. So we cannot rely on that. Fortunately, it is already known. If you look at the user space graphics libraries, they have been already tracking which part is updated and which part is not updated, so that they can just operate based on which part is updated. So in our case, we have been using Tizen for wearable devices. So the X window system has been already tracking which part is updated. So we just need to reuse that information for the hardware and the kernel. So if we just introduce some additional information channel for kernel, so that kernel's graphics subsystem is aware of which part is updated, and let the kernel control the hardware accordingly, then we can save power based on this information without looking at every frame. So this is example how it works. So the left-hand side is the previous frame, and in the center, that is the supposed frame, which is going to be shown in the next frame. So the update part is shown in the right-hand side, and you can see that only the clock hand, one clock hand, and an icon of alarm clock is shown. So that is the updated part, but because we are supposed to give the inputs as a rectangle, we are sending the information in the dotted rectangle here. Then the result concept is shown here. Like the arrows drawn in green is the abstract information. Like they are just sending the updated region sorry, and the red arrows shows the full frame is sent. So before our approaches, between hardware and kernel, we were sending all the information required to draw a frame. With LPD applied, we can let them send the updated part only so that we can save the bandwidth and save the energy. Well, the idea seems so simple. Well, we just need to get which part is updated and let the hardware control based on these updated parts. However, when we try to implement this for actual commercial devices, there were other problems. So, well, this is kind of administrative, non-technical problems like how to co-work with multiple departments and multiple layers and even different companies. And we needed to keep the software compatibility so that we don't need to rewrite any application or rebuild any applications. And we also needed to keep the old OS components so that we don't need to rebuild them. And by introducing this approach, we introduced non-determinism in the graphics stack. So the duration required to send each frame is now non-deterministic because the size of the updated frame is changing. So after introducing this, we have experienced more severe screen tearing prevention problem because screen was tearing a lot with these approaches. So what is the screen tearing? It is shown in this picture. So if we were trying to show this calling image in the center, if screen tears, then you will see the both frames at the same time. So both previous frame and the next frame is turned and they are shown at the same time simultaneously. So we are getting some screens broken. And we needed to tackle this based on the information from the graphics stacks. Okay, and some details on how to solve this problem was written in the paper, so you can refer to that and ask questions later about that. So, how good was it? So, how much energy is saved? This is our experimental result. So, when we try to use the smallest part, like one single clock hand or a single digit on the screen, it could save up to 7 to 8% of the total power. Here, I'm not talking about the power consumed by the display itself. I'm talking about the power consumed by the whole device. So the power consumed by CPU or network devices are also included in this frame. So when we try to benchmark with real applications in Tizen, we could save up to 2 to 3% of the total power, which can be translated to some hours of usage time because our devices could last like 3 days for a single charge. And another aspect is the overhead. If the overhead consumes all the benefits, then it's useless. However, when we have tested with full frame updates, which gives no benefit to LPD because it is required to update the whole frame if the whole frame is updated. And the LPD executes unconditionally, so even if there's no benefit, it is executed. However, when we measure the power consumption while there is no benefit, the power consumption has not increased, so there is no visible overhead in power. It is just because because LPD does not introduce any heavy loops or any heavy API usages, so it is not counterintuitive. We require no additional hardware components, and the applications or other OS components does not need to be updated or rebuilt. And we have uploaded the related source code at opensource.samsung.com and tizen.org as well. And the code related with Linux kernel is being upstreamed, so you can just download the mainline kernel to use LPD as well. I think some part is not yet upstreamed. Some part are waiting for reviews, but I believe that we can upstream the whole part within this year. So aside Kernel, when we look at the changes in the user space, it is also simple and quite intuitive. So for the DRI interface, we have just changed one function call without any overhead. And in the X video driver, we just added one more function call which does simple arithmetic calls. So there's no heavy overhead introduced here as well. So it is easy to maintain, and we expect that we can upstream these codes into the mainline of X Windows system as well. So the changes in Kernel, which is being upstreamed, is the updates in the graphical framework, which is called Direct Rendering Manager, and we have updated its device drivers as well. And another benefit of LPD is that it is orthogonal to other display power saving mechanisms. So we can just enable LPD while we are using the other power saving techniques in display as well. So if you are using ARM hardware and you are using ASTC or APVC or any other ARMS techniques, you can still use LPD over that and enjoy the benefit, additional benefit. So what we have learned with the implementation of LPD is that we may still have optimization points requiring simple ideas. LPD is just using the updated regions of the frames. So the idea is simple, and we may have other optimization ideas that is quite simple. We still need cross-layer optimization in graphical stacks because there are some information that are required by hardware or kernel, but the information is just residing in upper layers like applications or middleware. So they may have some ideas or information that we need, but they cannot use. Additional point with RPD is that we may need to educate the app developers. For example, if an application draws the whole frame for each time, then RPD cannot save any power. If the application is drawing small part in the frame, even in that case, if application declares that the whole frame is updated, then it becomes userless. So we may look at the application developer's behavior or even the graphical user interface designs as well. So this concludes my talk. And is there any questions or comments?
Oh, we don't have somebody going in the back. All right, I'll ask. So I was a bit confused by your tearing example. So you said, okay, your display 1 minute is showing the calendar, I guess, and the next minute it's showing an incoming phone call, and it inadvertently shows you both. And I didn't understand how that happens. It seems like everything has changed, so even if you're forced to do this delta thing, you should basically say everything has changed and you do the new one. Why? Can you go over that again?
Yeah, it is because change requires time. You cannot change the whole frame at the same time. You are changing one pixel by pixel. So while you are changing it, and the display panel wants to read the frame, and it is faster than writing, then it happens.
So it's incrementally updating.
Yeah.
Okay.
And they are hardware, so you cannot control it by CPU.
Okay. Any other questions? All right, let's thank the speaker.
Thanks.